Okay, let's talk about the washer method. So we'll have, at least in the most basic case, some region here, some function of x, and then another function of x. And we're going to have some area bounded between them. So we're going to have, like, for example, in this case, this area here, ooh, that little sliver rotated around the x-axis. So if we draw just a little tiny rectangle here, look at this little rectangle, imagine that rectangle rotated around the x-axis. That would give us this washer. Think like when you're putting together your IKEA furniture, you've got your bolts, your nuts, your washers. So, like, if I were to draw this guy sideways, a washer, two circles where the inside has been cut out, and it'll have some thickness here. So this little thickness here will be some delta x, and we'll have two radii. We'll have some inner radii, maybe we'll call that R1, and some outer radius R2. And then we're going to find the volume we get by taking this area here, rotating it around, in this case, the x-axis, so we get some shape that looks like this. Notice it's got a cavity on the inside. All of this stuff inside here is empty. So with the washer method, we're imagining taking a whole bunch of washers, like right here, we would have a small washer. Here would be the bottom of my curve. I would have some small washer that only goes to here. So this would be my inner radius right here, and this would be my outer radius. Oh, I went too far right there. Okay, so you see that little washer, some little thickness, delta X, and we're stacking all these up. So imagine like getting a bunch of different size washers, stacking them all up, and building this volume. Okay, so then what will that volume be? Well, it will be approximately the volume of one of these washers. Well, I should say it like this, it'd be approximately the volume of all the washers added up. So what's the volume of one of these washers? So again, I've drawn this sideways so that we can look at it a little better. Call this R1. The radius to the outside is R2. Remember, everything inside here is empty. And here's some thickness here. Maybe we'll call that thickness H. Then that's the same as if we had a full cylinder of radius R2 and we subtracted out minus that inner cylinder. And again, I'm drawing everything horizontal because it's honestly, it's easier for me to draw. So imagine you've got this full cylinder, this disc, and you cut out the middle, you'll get this. Okay, well, I mean, this is just a cylinder. We know this guy's volume. So his volume is area of the base times the height. So that guy's volume will be pi R2 squared H. And this guy's volume, calling V1, will be pi R1 squared H. So then the total volume of the washer is just big minus small. So that will be pi. I can factor out an H also, but I'm going to write it over here. R2 squared minus R1 squared, all times H. So I just took big minus small. I factored out a pi on the left and the H on the right. And then, so the total volume is approximately equal to the sum of all those washers. So let's call that VI. And then we, just like always, take the limit as H in this case goes to 0. That turns into an integral. And we end up with this formula. Okay, so what I want you to think when you're using the washer method, dx here, that's your thickness. That's what we're calling, what I called H up in those pictures, the thickness of each washer, not height. This guy here, f of x, we might call him R2. That's the bigger radius, and g of x is R1, the inner radius. So in general, if we're rotating around the x-axis, I'm going to have two different curves, some f and some g. Ooh, maybe he looks completely different. From some starting point A to B. And we're going to take this area, let me color code this. Take the area in between them and rotate that around the x-axis. And the way we're going to find the volume is by building up these little washers. So I'll pick some x value here, and I'm going to have some little rectangle here. So that thickness there is some delta x that gets rotated around. So imagine just that little rectangle getting rotated around. So I'll draw him over here. So be some outer radius and some inner radius. And I'm not good at drawing these 3D. That has some thickness, delta x. So again, we're imagining taking that little red rectangle there and rotating it around here to build a washer, and then we're stacking all those washers up. If you understand conceptually where all the formulas come from, you're gonna have a much better time. Notice here that my thickness of my washer is in terms of x. It's a delta x. These are delta x thick. That tells you immediately that you're integrating with respect to x. If you're stacking all these washers up along the x-axis, you're going to be integrating with respect to x. Whoever is your delta is your variable of integration. We're going to get to cylindrical shells in a couple of videos. Everything's backwards there. So this is the thickness of a shell. And when we take the limit as delta x goes to 0, this is the outer radius, the top of the rectangle. This is the bottom of the rectangle. And so this right here inside the integrand here is just the volume of one of these little washers. And then we add all those up and we get the total volume. Okay, so here's an example. We've got this region bounded between f of x, y equals x, and y equals 1 over x. And we're going to take that and we're going to rotate around from 1 to 4, rotate around the x-axis. So we get a shape that looks like this. Every single time you want to draw, always draw the picture, draw your shaded region. Always. Try to draw the volume. This can be difficult. Like I have a lot of trouble trying to draw this. That's why I'm using so many pictures from the book. I'm not a good artist. I'm not going to be able to draw this very well, but you try to draw it. And then absolutely every time you want to draw one of these representative washers, always come in here, pick some random x value. Here's some x value. Then here's that little slice of that washer that's going to get rotated around. And then you got to imagine, so that has some delta X thickness. You got to imagine all of those stacked up. So I'll try to draw this guy here. And again, I'm going to try to draw this in 3D, but I'm not very good at it. Okay, so I've got some washer there. Kind of looking at a side view of it where this inside here, the middle was cut out. That middle was this chunk in here. This is this. I just want to make sure you understand what my picture is. And this is some delta X thickness. That's going to become my DX. And then I need the two radii. So here's the X-axis coming right through the middle. This top, what we might call R1. I want to be consistent. How did I say it up here? I called it R2. The top, that's just F. That's X. At location X, my top is also X. And then my bottom, what I called R1, the inner radius is G, and that has a height of 1 over X. So you pick an X value, that distance right there is 1 over X. So then the volume of just this washer, that guy's volume, I'm telling you, if you go through all these steps on every one of these, if you write out the volume of one of the little washers, you're not going to think, oh, I got to remember the formula and which formula and who am I integrating with respect to. If you draw this out, you're going to get these right. So that volume is going to be pi big radius squared minus little radius squared. Get that a little prettier. Times my thickness, delta x. And then we're just going to add all these up. So when we take the limit as delta x goes to 0, a sum is going to turn into an integral. We're going to get this formula. So I'm not going to go through all the steps of actually doing the definite integral. My main goal in this video is teaching you how to set up the integral. So big radius minus small radius. Don't memorize, oh, it's, well, f squared minus g squared, because f and g might change. Our radii could change. Okay, let's look at another example. Okay, so we're going to take this region here and rotate it around the x-axis. Okay, so we're going to draw in, pick some random x value here. Here's going to be my little rectangle I'm going to draw in. That's going to get rotated around. So I'm going to have some washer. It's going to look like this. So I'm just drawing like a side view of it. See, I can try to draw this in. Maybe that's an okay picture. Okay, that is going to have some little thickness, delta x. That's how thick it is. As soon as you write your delta, you know who you're integrating with respect to. I'm integrating with respect to x, so all my variables have to be x. I can't have any y's in my integral. Everything needs to be x. Okay, my outer radius to the top, right there. That height is x squared, the top function. No, it's not. Oh, see, I tricked you. I looked at it wrong. The top is y equals x plus 2. The bottom is x squared. So then the volume of just that little washer, that guy's volume right there, will be pi big radius squared minus little radius squared times delta x. Then the total, like we could write this out. So I could call this VI, I could call that XI. Then the total volume is the sum, is approximately the sum. I equals 1 to n because we've imagined that we drew out n different little washers here. So this would be the sum. I equals 1 to n of pi xi plus 2 squared minus xi squared all times delta x. And then we take limit as delta x goes to 0, which is the same thing. That's the same as taking the limit as n goes to infinity. So instead of only doing n little tiny washers, we do an infinite number of them. If we're doing an infinite, they all have to be infinitesimally thick. So that means delta x goes to 0. And when we take that limit, this sum turns into an integral. That approximate turns into an equals. Start to finish, I got to figure that out here in a minute. And we'll have x plus 2 quantity squared minus x squared. And when we take the limit, that delta x becomes a dx. Okay, now we got to find our limits. Now we can just look at the picture and see it's negative 1 to 2. Why am I using these limits instead of these limits? Because I'm integrating along the x-axis. My delta was in terms of x. Everybody needs to be x's, even my limits. Okay, now if we didn't have the picture, how would we find my x limits? Because I want the region in between these curves. I just see where the curves intersect. So for the limits, we're going to set these two guys equal. I'm trying to find these points right here, trying to find those x values. So get everybody on one side. That's a quadratic. You're in Calc 2. You should be able to factor that in your head. And we get negative 1 and 2. So those will be the limits. And now we can, I think we got space here. Yeah, we could probably finish this up. Okay, so that will be, I could bring the pi out front. The definite integral from negative 1 to 2. X plus 2 squared. I don't need that parenthesis because I'm going to distribute everything. X plus 2 squared is x squared plus 4x plus 4. And then bring down that minus x squared. Don't forget that pi. X squareds are going to cancel out. That's pure coincidence. That's not always going to happen. You are often going to get a bunch of cancellation, but not every time. All right, so now we do the integral. That will be, let's see, 4x squared over 2, so 2x squared plus 4x evaluated from negative 1 to 2. So plugging in the top, we're going to get, I think we get 8 plus 8. I think we get 16. So let's check that. It would be 4 times 2 plus 4 times 2, 16. Plugging in a negative 1, remember it's always top minus bottom. I'm going to get 2 minus 4. 2 minus 4, so that's negative 2. So I think we get here 18 pi. You guys definitely go through and check all of my calculations. Make sure that's correct. And cubic units, whatever our units are, I'll write here. Units cubed, because it's a volume. Okay, what if we're rotating around the y-axis instead of the x-axis? If we're rotating around the y-axis, we're going to have vertically stacked washers. Because my volume I'm looking at is going to be symmetric around the y-axis. With washers and disk, whoever you're rotating around, that's your variable of integration. If you're rotating around x, you have washers stacked along the x-axis. If you're rotating around y, you're going to have washers stacked up. So now we're going to have, instead of top and bottom functions, outside and inside functions. So in general, you're going to have some outside function, meaning furthest away from the y-axis, that we're calling u here. So I'll have some u here, and then I'll have some v that's closer in. Ooh, maybe it looks like that. And then we're going to have some limits here, c to d on the y-axis. So we're going to have some region that looks like this, rotated around like this. So we're going to get, again, I'm not very good at drawing these. We're going to get something that kind of looks like this, where we have some cavity in the middle. This whole middle chunk here is cut out. So our washers now, I'm going to erase all this to get it out of the way. Our washers are going to sit like this. So imagine this little blue rectangle rotated around. So the other chunk of that blue rectangle would be over here. So now it's coming out at your eyeballs. It goes back in. You get some washer that looks like this, where the inside is cut out. That's going to have some thickness, delta y. So we're going to be integrating with respect to y. And we'll have our outside radius. Don't think top and bottom. You got to think outside and inside. The outside here we're calling u, and the inside radius right there we're calling v. So it's big disk minus small disk in volume. Okay, let me erase all this so when you have these notes later, you won't have all that stuff in your way. Okay, so we're going to do one of these problems. That is this one, number 101. Okay, so I went ahead and grabbed the picture. This is a problem from the book. I went ahead and grabbed one of the pictures from the solution. You know, if you click on the little blue here, it takes you to the solution. The answer was right under there. I did this because I'm terrible at drawing these, but you do want the ability to draw these. Like you're going on a test, you would have to draw this on your own. So let's think, how would you draw x equals e to the 2y? Because you've never been asked to draw a function of y instead of a function of x. X is a function of y here. So let's kind of think this through. If I had this guy, where I've swapped the x's and y's, technically the inverse of that. If you swap x's and y's, you've got the inverse. We know his graph is going to look like this. It passes through the 0.01. That's not going up, that's going down. Remember, all a function and its inverse do is they swap along the line y equals x. So the inverse of this, that guy right there, is going to be that flipped over here. It's going to be something that goes like this. It's a log, if we were thinking in terms of functions of x. That's this graph right here. That's this one. X equals y squared. You should be able to figure out what x equals y squared looks like, right? Instead of y equals x squared, it's x equals y squared. And then the horizontal line, y equals natural log of 2. So we're bounded in between those three, or these four, and the x-axis. And then we're going to rotate around the y-axis. So I'm rotating around this way. So we build one of our washers. We draw in here, we pick some random y value. That's going to be some delta y thick. And imagine rotating that around again. If you try to kind of draw it out, your picture might be terrible. We're just going to have a little tiny hole cut up there. You can see up here, we're going to have a bigger hole cut out. So you can, one way to do this is to try to draw the opposite side over here. So this region, let me try to draw this whole thing in red. This is what the volume will look like, but it'll be coming out at our eyeballs. Here is the red. And here's one of my washers here. So he has some thickness delta Y. We're stacking up a bunch of these washers, and you can see as you go up, the hole in the middle is getting bigger. I hope you can visualize that. Again, I know my pictures are terrible. So I'll kind of draw him over here on the side. I like to kind of do this game, draw like a side view of that washer. Here's some delta Y. My inner radius and my outer radius are going to be what? Don't think top and bottom. You got to think outside and inside. My outer radius, everything needs to be in terms of Y, will be this curve here. E to the 2y. My inner radius here, the radius of the hole cut out in the middle, will be y squared. Okay, then my total volume, I'm not going to go through the work of writing down the Riemann sum and all that, is going to be my integral from smallest to largest y values. I'll get to that in a minute. Bigger radius, pi, don't forget my pi. Bigger radius squared minus smaller radius squared dy. Okay, now what are my upper and lower y's? Everything needs to be in terms of y because we're integrating with respect to y. We're starting down here at y equals 0, and we're going up to y equals ln of 2. And I'll even put on here, these are y equals. And remember up here on this last one, these were x equals. I'll put that on here. Okay, now let's do the integral. So that'd be the integral from 0 to ln of 2. I'm going to bring the pi out front. Raising a power to a power, we just multiply. I left off my squared here. I apologize. You guys are probably yelling at me right here. This was y squared squared. I said it, but I didn't write it. So minus y to the 4th all dy. Okay, and now pi just comes along for the ride. Antiderivative e to the 4y will be 1/4. I'm just going to put it over 4. That'd be e to the 4y. over 4. Antiderivative of y to the 4th dy will be y to the 5th over 5. Evaluated from 0 to ln of 2. And I'm just going to dot this because let me see if the answer does clean up. Hold on, I'm going to pause. Okay, yeah, the answer does clean up a little bit. So, like, feel free to skip ahead through watching me do all this arithmetic, but here's what we're going to get. So I'll go ahead and do that just for completeness. Okay, so a better way to think of this, because I'm going to be plugging a log into an exponential, and logs and exponentials cancel each other. I want to think of e to the 4y as e to the y raised to the 4th. That's going to help when I plug this in, because then that pi is going to come along for the ride. I'm going to get e raised to the ln of 2 to the 4th power over 4 minus ln of 2 raised to the 5th power over 5 minus, I got to plug in 0. This guy ain't 0. He'll be 0. He's not. E to the 0 is 1. So I get a 1/4 minus 0. E to the ln of 2 is just 2. Let me make this a little smaller. So e to the ln of 2, e and ln cancel each other out. We get 2 to the 4th, which is 16 over 4. So we get 4 minus ln of 2 to the 5th power over 5 minus 1/4. So it'd be 15/4. 16/4 minus 1/4. Is that what they got? Looks like they got a common denominator. Yeah, that's going to be the same thing. So that's 15/4 minus ln of 2, all raised to the 5th power over 5. If we get a common denominator here of 20, multiply top and bottom by 20, top and bottom by 4, and then they factored out that 1 over 20. That's where they got this. That's weird notation. What they mean there is ln of 2 to the 5th power. Okay, that's a good place to stop in this video. Let's circle that answer. And of course, units cubed.